I whole my life I've been doing working on databases. 25 years on Oracle. About 7 years ago, I fell in love with Cassandra. So I was tasked for today's session. I wanted to discuss about NoSQL databases. In past 6 sessions, so I want to start with saying what is NoSQL databases. First of all, I want to show RDBMS is apples, let's say, right? We always have this nice comparison of apples versus oranges or something like that. So all RDBMSs, I'm calling them apples because they're similar. They function based on the similar rules. All RDBMS share similar functionality. And we cannot compare that with NoSQL. On the first slide itself, I want to be very clear. We are not here to argue which one is better. I'm just showing you what is possible with NoSQL. And then every application has to do their own analysis of which NoSQL database is suitable, if at all it is required for their application. So again, as I said, RDBMS is a bunch of apples, whereas NoSQL is completely different, and there are no apples. They're just everything else in fruit section. So comparing them apples to apples is not possible. Okay. Now let's go into the next section where I tried to put one slide. It is very difficult to show how NoSQL databases have evolved. But what I'll do is I'll point out few important ones here in the timeline. So mostly before 1990s, we know about RDBMS and other technologies like hierarchical databases or file system-based databases. Not much in between 1991 and 95. There are a couple of very beginning of open source GNU licensed databases. And also there was one database like using SQL. SQL was pretty standard in those days. And there was all the databases which were developed were thought like, if you don't support SQL, there is no way we are going to use that database. But 1995 onwards is when the mindset has started to change a little bit. And in 1998, there was a person called Carlo Strozzi who first time coined this word called NoSQL. But remember that in 1998, the NoSQL was attached to a RDBMS product, not a non-SQL what we know today. Okay. Now the first ever database which came out, which was in a graph format. A little later in the presentation, we'll see what are the different types of NoSQL databases. But for now, just note that in 2000 itself, we had Neo4j, and this is a graph database which was introduced in 2000. So way early on in the game, even though the NoSQL terminology was not even standardized, the first graph database we ever know is already introduced to market in 2000. Which is Neo4j. And then there are a couple of other big things which came out in 2004. Google Bigtable was introduced. But little later, we'll talk about Google Bigtable again. In 2006, Hadoop came out. And if you look at this whole slide, there are like a couple of colors I have used. Like the black color is the regular stuff. Red color is a little bit you have to notice. And then there is a red color with bold letters, which is, we have to notice that this is all NoSQL. We have to notice that this is all NoSQL. And then in 2006, Hadoop, I have written in a big font, red color, because Hadoop changed the entire big data platform. So 2006, when Hadoop came out, the entire big data platform has changed because Hadoop was developed in Java. It brought out this distributed computing platform. And Hadoop ecosystem itself, if you think of anything today which is open source, most likely it has roots attached to Hadoop in one or the other form. Now, So in 2006, as I said, Google Bigtable reappears because what happened in 2004 was Google Bigtable was introduced, but they never released the research paper on why they created Bigtable, what is the theory behind it, and all the detail was never shared. But then 2006, Google came out and they published the research paper, why they created Bigtable and what was the reasons behind it, the ideas behind it, and all that. Now in 2007, Amazon Dynamo research paper came out. You see how the research paper is mentioned in brackets is basically, informing you that there was a research paper and then there is a product release or something like that. In 2007 was the first time MongoDB, a document database, which is very popular today. And most of the other document databases like CouchDB, we don't even look at them because Mongo is so good with documents. We'll talk about all these different databases in a second. Here we are just trying to get a landscape of what happened in past 20 years. 2008, Apache Cassandra. So what happened is somebody at Facebook took the Google Bigtable and Amazon Dynamo, and they merged both of these products. Whatever is good in each product, they put it in one place and they called it Apache Cassandra. In 2008, Facebook made Apache Cassandra as an open source. Cassandra was in-house developed at Facebook, but they released the entire open source code to Apache project and made it open source. And then you see there is a CouchDB, which appeared in 2005 as a document database, but then in 2008, it became open source. Then in another 1 year, next year, 2009, we see the key value store, which is Redis. And today, then you see there is a CouchDB, which appeared in 2005 as a document database, but then in 2008, it became open source. Then in another 1 year, next year, 2009, we see the key value store, which is Redis. And today, Redis is very powerful in sense it's not only key value, it has a Redis cache, Redis time series. There are other products available along with that Redis database. Or in general, the product Redis has other flavors of it. Then there are other products like React. If you see, that's a Dynamo-inspired database. And Hadoop also, in its ecosystem, it has something called HBase, which was introduced in 2009. Now, 2009 or so, when, already there are a few products in market, which are graph databases, document databases. Eric Evans, which he started in 2009, he reintroduced the word called NoSQL. So first time NoSQL, when it was introduced to market in 1998, it was attached to RDBMS, and it was nothing to do with today's NoSQL databases. In 2009 is when Eric reintroduced this NoSQL word, and we'll see in a bit like what does NoSQL mean, why did it actually catch up and all. But in 2009, it gave an official name to this technology called NoSQL, which is non-RDBMS style databases. Then you can see a little bit like in 2011, we have Apache Druid, which is a time series database. And Apache Druid is actually evolved into, you can do other things with Druid instead of just time series, it can do other types of databases too. And then I put like a later slide, I'm going to show you how many databases are in NoSQL space. But I just put the main important ones to notice are on this list here. So this list is not comprehensive list. It's a very hand-picked few of the very important ones in place. Doesn't mean that these are the only databases available. In 2019, most recently, Amazon created a document database, which is kind of MongoDB, but it's Amazon RDS kind of offering. So this gives you a little bit of landscape of what happened in 20 years and how the NoSQL has changed everything. But 2006, Hadoop is the most important in the whole story because Hadoop brought out that open source and distributed computing kind of platform or the ecosystem. Okay. Moving on. Now, there are two slides which don't fit into the whole discussion, but they're important. And I just throw these slides in random place because we need to have this discussion before going into distributed computing. What is vertical scaling or scale up? These are the two words we use in the industry. What we used to do, this was 20 years ago when I tell the same thing, they used to think, oh, this is perfect. We don't need anything else for the rest of our life. If at all we need more compute, we just have to add extra CPUs onto the existing server. And if we need more space in the memory, we just add more memory sticks, right? Now, vertical scaling was the only way we used to scale in 1990s until 2000s. The reason was hardware was expensive. We were not able to buy so much. We just start with a basic server, expand it to whatever maximum, then replace the whole server. That was the whole vertical scaling was. The problem with this was there is a limitation on how much you can scale because every server has a motherboard which has a limitation of how much RAM it can accept and how many CPUs it can accept and the type of CPUs. So this is still we are talking about like having single servers for our infrastructure, like one web server, one database server, things like that. Then came the terminology where what if we take instead of one server we take multiples of those servers and make them horizontally scale, or we also call it a scale out. Basically what happens in this is you buy low cost commodity servers, and basically instead of having one server you will have 4 servers or 10 servers or 20 servers, and these are not high cost servers, these are like basic servers, but run them in a single cluster, like a huge cluster. You can start with like say 4 node cluster, you can go up to 10 nodes or 20 nodes. And then later on, we'll talk about multi-data center, active, and all that other things. But what horizontal scaling means, now instead of one server reaching its limit, what if you had multiple servers, similar ones, and they all work together as if it is a single cluster? Yep. Now, this is where Oracle introduced something called RAC, Real Application Clusters, where instead of running one Oracle database on one server, instead now we are running 4 instances on 4 different servers, but they're acting like a single cluster together. So this is when horizontal scaling came into picture, and then as I said in 2006, Hadoop changed the whole thing. They instead of calling it as cluster of 4 nodes, now we have Hadoop can support. Right. So we have to look at a couple of other things also. We, in past 30 years, I would say the RAM capacity has gone up, the storage capacity has gone up. At the same time, you see how much compute speeds have gone up, right? Now, let's say back in 2005 or 2006, we have a desktop. Now your phone is more powerful than that desktop. So similarly, on the server space, even network speeds went up. We have gigabits and 10 gigabit network speeds. So according to the whole technology, the whole communication on the network, latencies and all those things have improved, meaning speeds have improved, latencies have come down. And because now we also have to think of Hadoop, what it told is, instead of doing everything in one place as a single server, single process, now you start distributing the job into thousands of places, and then thousands of servers are acting independently on their own, but they come back and give you the single answer at the end. So overall, we have to look at all the infrastructure components have become more powerful and more cheaper. That way we can actually increase our clusters in size, like buy more hardware, or even talk about like, AWS EC2s, like virtualize the whole thing. And now we are talking about Kubernetes, even further orchestration of virtualized servers, right? So in general, what happened is the past 30 years of transformation, whatever we were doing very slow, now we are able to do the same task very, very fast and on thousands of servers in a distributed manner. Once you get to how the databases have changed with the NoSQL introduction, you will see much more analogy of why horizontal scaling has changed the whole infrastructure, because we don't want to have 4 servers only. Instead, we can have like 4,000 servers in a cluster. So we'll talk about it as we go. Okay. Initially, when we started talking big data, like I would go back to 15 years ago. We started talking about big data. There were only 3 V's. Now, this is mostly theory, but in general, what is big data? Why did we call it big data? Is you see how fast the data is coming in, which is velocity, the speed of data flow from your systems. Like you have multiple application systems or multiple different systems, they're all sharing data, or they're all pumping data into the database. It could be one database or multiple databases which act like your application in the background. Yeah. And the amount of data we started collecting, especially with the Internet of Things. Now, imagine many of us have smart lights today. Using our Wi-Fi from your cell phone, what you're doing is you're switching off a light or switching on a light, a fan, or you're, in one room, you're making all those lights blink, change colors, stuff like that, which is all called Internet of Things. All these small devices today, forget about like very smart fridge and very smart washer dryers. Very simple things like even lights are connecting to Internet today. So we have huge amounts of data being generated, which is the volume. Then we have diversity of type of data. Like, basically we have like, if you look at YouTube, how many videos are uploaded every day? They say like one day uploaded videos on YouTube, it will take like some 20 years to watch them if one person wants to watch. So that much of video data is being uploaded. So this is only video, right? Then you can look at Spotify, where the audio kind of data is being uploaded. So we are generating a diversity of type of data, and this has increased since Internet has become very easy to use. And this is about past 10 years. Internet speed has increased everywhere. And now imagine your cell phones are contributing to this data, because even cell phone consumption of data has increased, meaning every kid, if you see, they're playing a video game or they're watching some YouTube videos on their phone, they're consuming a lot of data, meaning there is a lot of data on pipe which is in flight, always moving from one platform to another platform. Then comes a very important topic is the quality and accuracy of data, which is also called as veracity. Now, if you don't have accurate data or the quality, data quality is not imposed, meaning you're like, pumping in junk into the system, obviously we don't have quality data in the database. In the system, meaning it could be application, it could be database. At the end, you're storing all this in a structured format in the database. So I'm just calling it as a store where you store all your data. And then recently, with all this data science and data scientists coming into picture, we have a lot of data. Now, what do you do with that data? That is the value we get or we can create out of the data. We have a lot of data. Now, what do you do with that data? That is the value we get or we can create out of the data for the business. For example, let's say, for example, recently in US elections, there are a lot of fake news. And if we cannot identify that fake news in time, the election result can change in a better or a worse way. So we have to create systems which can identify the quality of data, use that quality to generate useful information for the business. So imagine the other use case I always talk about is like, say, fraud detection. So Visa, MasterCard, American Express, these people have to identify the fraud happening while it is happening, instead of waiting for 20 hours, after which we will generate a report saying, oh, there was a fraud using these million credit cards, happened somewhere in the world, right? That is not useful after 20 hours because the fraud has already taken place. Money has already moved from place to place. Now, these 5 V's, basically, you can think of it as pillars for the big data. And these, in general, can be for anything, not just big data, but any system which is generating data, it should always look at these 5 V's. Technology NoSQL was introduced is when it was introduced about 10 years ago, like 2009. Non-SQL, meaning we not only can do SQL, but there are other ways to interact with your database. This is specific to database. So you have to go back 20 years ago where we all had only one way to interact with database was structured query language. And if your database did not support structured query language, we did not even consider that as a database. You say, oh, you know what, I'm not going to use this database because it's not easy to work with. But then the new generation programmers have come out, like, 1999, 1998 time, Java was introduced. Many of the databases today, about 90% of them are developed in Java. So when these Java developers came up, there are many good programmers who just did not write Java code. Instead, they wrote the whole database in Java. So what they said is, you know what, my whole concept of writing a database was I can do my Java code, so I don't need SQL to interact with my database. So they said not SQL or non-SQL, meaning there is another way to interact with the database. And it is not only SQL, there are other ways. We'll talk about each database has its own interface to talk to database. And then there was also relational databases also had this issue of, we talk about chord rules. We say, okay, first normal form, second normal form, third normal form, and then you know that it is denormalized. So in several use cases, we actually don't want the relational tables, meaning we don't want two tables. Instead, everything is written in one place. Normal form, second normal form, third normal form, and then you know that it is denormalized. So in several use cases, we actually don't want the relational tables, meaning we don't want two tables. Instead, everything is written in one place. So you can read everything you need in one shot. So that means we were already at the end of RDBMS, it was about 15 years ago, we started to see that we are designing our databases without relations. So NoSQL databases focused on this non-relational technology where they say, you know what, if you need something, just store it multiple times. Our storage has become cheaper, and now we are able to keep multiple copies of the same data. So do not relate them using two different tables. Instead, store everything in one place in non-relational models. NoSQL databases also came up with one more wording called no schema or flexible schema. Basically, they said, you know what, schema is actually very limiting to me. I'm not able to store something new tomorrow. So we need databases which will have no schema, and then it will allow me to do flexible data storage as it comes, as and when it comes. And let's say, for example, the very simple example is there is a customer. I don't know the age of the customer. So at this point, I'm not going to store the age, not even storing null for that column, right? There is no column called age in the database. But let's say after 3-4 days, I get to know the customer's age. I will store it. There was no column assigned to it. So this was where the concept of no schema or flexible schema came. But then, eventually having a schema is a good thing. Then you don't have to do the guesswork of what is the data type and all. In general, NoSQL databases are simple in design, meaning their architecture is simpler to work with. They all support horizontal scaling one way or the other way. We'll talk about CAP theorem and see why a database favors availability versus consistency or whatever. So 20 years ago, we already had an issue of availability, meaning if you had one server, that server goes down, your system is not highly available. this was already a problem in the market. So we wanted to have our NoSQL databases already be very fast. Obviously, we are using multiple servers to give that fast thing because it's a distributed computing platform. And we should make them highly available, meaning we should not have single point of failures, whether it is storage, database, or network. You know, we were talking about the network, let's say communication issues between the servers. How do they impact? So each database has their own way of dealing with it. But in general, all NoSQL databases, they were designed to be fast and highly available. So let's move on. And here is the slide to introduce some of the different types of databases we have under NoSQL. So RDBMS is just RDBMS. NoSQL databases have different types of databases. So it is very important for us to understand how to use these databases because there are 4 different types, 5 different types, or many more. But we need to understand how they store data and is it suitable for my application or not. Now remember one thing, in 20 years ago, we used to have one database, one application server kind, like understand how they store data and is it suitable for my application or not. Now remember one thing, in 20 years ago, we used to have one database, one application server kind, like say for example, we used to use WebLogic or let's say Apache Web Server, something like that. And then we had one database called Oracle, okay? Or let's say DB2. But we never had systems where we had multiple databases for the same application. But today, if you go look at how every organization outside, whether it is small or big, what they do is they're not relying on one database, but what they do is they have multiple flavors of different databases, and they store their data in different places because each of them can give that performance and stability and other use cases which are suitable. Like, say, for example, something is not suitable for Oracle, they store it in Elasticsearch. This is an example. Or they store data in Oracle as well as Elasticsearch, but your application screen will bring data from 2 different places, depending on what it is looking for. And each database is performant based on one or the other type of data. So here on this slide, I'm trying to introduce you to 4 different kinds. There could be more kinds, but first we'll start with the document store. Later in the slides, I'm going to introduce each of them again with more detail. But what you see is the document store is a database, a type of database where documents can be stored. Instead of storing as row column, we will be storing the entire document. Let's say, for example, a purchase order. A user comes in, give me the entire document for that order. Okay. So in one shot, you get the entire document, and then you do whatever you need to do in your application, whether you're displaying it or you are interacting with the user or showing the order details along with what is the shipping dates of the items. Let's say Amazon order, right? Now there are some examples I have put there, which are Apache CouchDB, Couchbase, MongoDB. These are like document stores. One thing I want you to notice and understand is whenever there is Apache in front of the database name or the technology name, that Apache generally says it is open source and freeware, okay? Meaning you don't have to purchase licenses. So there is CouchDB and Couchbase are completely different, 2 different things, but they both do document stores. And also, if you see in a race of after 10 years, now MongoDB is most popular in that space. Okay? Doesn't mean other databases don't exist. They are still there. There are many new ones being created. Like I was talking about Amazon Document DB. After 5 years, we have to come back and look at this slide and say, hey, how many of these things are gone now, right? Then we move on where we have key value stores. Now, key values are very very basic structure, like there is a key and a value. Let me give you an example. Your SSO username and the password. The key is your SSO username, and the password is whatever the password is, whether it is hashed or not hashed. Then for the same SSO username, you can also have, let's say, what is the employee start date? Let's say I joined in September 2001 or 2003. What is the date? So you can say, for example, employee date of birth, right? The key is the employee ID and the date of birth is the value whenever they were born. So these are very small key value stores. Don't think they're small databases, because you can have an entire set of key values, huge amounts of pairs stored inside the database. But these are extremely fast databases, meaning most of the time we are going to put them in memory and your queries run in memory. They don't have to load anything from the disk unless there is some new values which need to be synced up. So some of the examples here are Dynamo, Redis, React, Memcached or MemcacheDB. So in this space, if you see, Redis and Memcache are the most popular ones here. And then there are many other databases which we don't have listing here, but there are there. Then we have graph databases. Now, in general, I want to tell you, among any of these categories, graph databases are the more complex ones. Very complicated data. The storage and query language is very complicated with graph databases. But the use cases they serve or they solve are very important use cases which are not possible to solve with any other kinds of databases. Graph databases are very special. Some of these examples are Neo4j, which I was showing you. It was introduced in 2000, and it is still one of the top leading graph databases in market. There are other databases. You can see the other names here, not very popular, but they're there. Then we come to a wide column store or a columns in market. There are other databases. You can see the other names here, not very popular, but they're there. Then we come to a wide column store or a column family store, which basically looks like tables. In our RDBMS world, we have tables, columns, rows. And these wide column or column family stores look like that. Okay. So only because of the look, do not take them as, oh, these things look like Oracle tables. Okay. And some of the examples in this area are Apache Cassandra and HBase. Now, HP Vertica is a commercial product. So don't think all of these products are free and open source. Like HP Vertica is commercial, very expensive, and it is not open source. Compared to Apache Cassandra is open source, and it can run on thousands of servers. We are not talking about a specific product here, but I'm just giving you examples of, okay, do not think all NoSQL databases are open source. Meaning we have commercial databases also in this space, and when they're commercial, they're proprietary, they're not open source. Okay? Moving on, I just want to show how big this landscape is. Let's say, for example, how many NoSQL databases are in market. According to wiki listing, there are like 200 plus, and they're growing nonstop. Like, somebody comes in and writes something called RocksDB. Okay. Then there is another company, a small company, which comes up and says, hey, you know what? RocksDB is doing this storage very well. Let me take Cassandra, store that data in RocksDB instead of using Cassandra's original database engine, right? And they create a new one. Okay. New databases are open source. People are able to take the open source code and emerge it, like, evolve it, or they can actually make it suitable for their own requirement. Now, again, this slide is just to be, so it is not a slide where you're going to read all these names, but it is just to show you that there are many technologies which are used as databases. Let's say Apache Flink is not a database, but it is on this list. These are all very important technologies which have changed the whole landscape for NoSQL or the open source databases. By the way, there is Oracle NoSQL also on this list if you see. This list again is not a full list. There are 200 plus databases, and most of them behave like NoSQL. Some of them behave like they mimic the RDBMS technology, and not everything is NoSQL in terms of how they behave. They were all created for a specific purpose by a specific company or 4 people or a single person, who knows. Elasticsearch is also listed on this. Elasticsearch is not considered database, but it is very high powerful data store, which is very well organized and indexed, so you can get your results very fast. So let's move on and take a close look at those 4 categories we were talking about. We talked about 4 categories. I'm going to pick an example of one database, show you a couple of different things here. So what I want you to notice is we start with a document DB. Most popular document DB or document store is MongoDB. On your left, you see the green text is like a JSON document, okay, which has key value pairs in it. There is an ID column which is internal to MongoDB, and there is all this data stored inside. That data is a single document. And then there is a black document which shows model, which is a car. Let's say it's a Volvo C70 made in 2007, and then other details about that car are stored in that document. Now what MongoDB does is you store everything as a document, and the document is in the format of JSON. JSON is JavaScript object notation. So they take the document and MongoDB converts it to BSON, which is a binary JSON document, and stores it inside. When you retrieve a document, you use the ID, but you get the whole document out. Imagine that's like a row. Okay, you get one row, you get one document here in MongoDB. On the right side, architecture diagrams, they're just for reference sake. They're not like really, I'm not showing you, oh, this is how Mongo works. But what it shows you is Mongo has an application. There are multiple servers, which are primaries and secondary. Secondaries are nothing but replicas. They are read replicas. Primary database servers are the primary replica, where you can do a read write. And internally, they all replicate data so that you have multiple servers under the covers, and they all act like a cluster. And together, they're all acting like a high available database. And application talks to the driver, and driver talks to the underlying infrastructure, which is the database infrastructure. When they build all these NoSQL database languages it supports, like you can see, if you're writing an application which uses MongoDB as a storage, you can write your application in Java, Node.js, PHP, Python, and so on. There are a bunch of other languages which are not covered here. I just tried to put the most popular ones in place, because we are all curious to know how the databases look like. Now I want to show you Mongo uses a query language which is very specific to Mongo, and I have highlighted that query language over there. Right? What you see just above that JSON, BSON, where I gave you the text JSON, BSON, above that there is a Mongo query where it says db.students.find. Student name is Jasmine Scott. That is how you query your MongoDB documents. Okay. So that's just a sample query, but there are very complicated queries you can write, and they don't look like SQL queries. They're very different. That is one reason we were saying not only SQL, right? There are other ways to query the database. So the idea here is I'm going to introduce 4 types of databases and show you a couple of examples of how they look like. And then we will definitely look at the consistency and other things we need to talk about. Now, let's talk about the next type. Okay, so key value stores. Now, Redis is one of the popular product in this area. where obviously it has a master and read replicas. Then you can have multiple masters. Your application can read and write data. Mostly, this is reading and writing data. Okay. So in the key value stores, do not think that all the data is just text data or the number data. You can see on the left side, I have given you some examples of what kind of data types this Redis supports. And it has very advanced data types like bitmaps. You have hyperlog log, and then Redis time series kind of data. So it has very advanced data types. Now on the right side, you see a couple of different types of data, how it looks like inside. Like if you are going to store a hash set, it has multiple things in there. The user ID is 1000, username is Entres, date of birth or birth year is 1997, 1977, and so on. And then in the second black window I'm showing you here is geosearch, meaning this database also supports geospatial data. So basically, there are many languages you can use as a client application. You can develop your applications using Perl, Python, Ruby, Rust, Scala, and so on. Redis is very different database. It doesn't look like a document. Or so let's look at graph database. Now, this slide on purpose, it was made complicated because I want you to take away one thing. Graph data is very important, very powerful. At the same time, it's very complicated. So this is an example of Neo4j. Each of these components or the nodes are called nodes and vertices and so on. It has its own terminology. What you can see in the background is a very complicated graph data. And the reason this slide is made to look like this is to let you know that graph is not easy to get in. It is very complicated data. And out of these 4 categories, graph data is the most complex one. Your code looks very different. It doesn't look like SQL anywhere. Like, if you look at the languages they use for Neo4j, we use GraphQL, Graph Query Language, and then Cypher, meaning there are multiple ways you can interact with Neo4j. And sometimes you have to use that GraphQL advanced API to talk to Cypher, in turn talking to Neo4j. And then there are very useful languages like Node.js or Python and Java, which can be used to interact with the database. They also have nice UI tools to interact with your graph data. But again, as I said, it's one of the most complex databases, but it is very popular because of the problems it can solve for your business. And then the little bit familiar one, as I said, wide column store or column family stores, which look like a table and rows and columns. The example I took here is whatever databases we have discussed about, we have like master and read replicas and so on. Cassandra is a masterless, meaning all nodes are masters, all nodes are workers. So they all can perform the same task. They don't have any special assignments like, oh, you can do read write and I can do all the reads and stuff like that. This is a peer-to-peer technology. It was completely developed in Java. The Cassandra query language is similar to SQL, but it is very special to Cassandra itself. The syntax looks same, but do not get fooled by that syntax. Data looks like columns and rows. It has its own ways of partitioning data, replicating data, and all. Now, any of these databases I've been mentioning, these databases run on multi-cloud. All these databases are evolved to run on multi-cloud, meaning one single database, you have multiple nodes. Some nodes in AWS, of them most likely are active-active. In Cassandra, all nodes are active-active. There is no passive nodes, meaning my AWS cloud here, the picture it shows In North America, we have Google Cloud. In Europe, we have AWS Cloud. And in Asia, we have on-prem. All of those nodes are single cluster, and meaning it's a single database. And it also is developed in such a way that, because in Europe, you have GDPR rules where the data you need to keep all the European data in the European data centers. They cannot flow out of Europe. And that is possible with Cassandra. The way it is developed, you can keep all your GDPR data in Europe, whereas your data is just sitting there, but you can access it from anywhere in the world. The four categories I was mentioning, I wanted to put one more extra category here called time series data. Now, some of these databases or most of these databases might support time series, but there are some databases like Druid which are specialized to store time series data. These are very special, and this Druid database is very advanced in that sense, meaning it can do streaming data, it can support batch data, it has deep storage, meaning you can archive some data and push it into deep storage, and deep store can be your HDFS or Amazon S3. This is a very advanced database. If you look at it, it not only supports your regular workloads, but it can support the time series data, and it uses Druid SQL. Did not put much information here, but you can read up. Time series is very important for the whole Internet of Things. Now let's spend a minute on this CAP theorem, because this is very important. All the NoSQL databases, when they were introduced, like back in 1998, Eric Brewer, he introduced a theorem called CAP theorem. He said, we can have consistency, partition tolerance, and availability. So any system, whenever you store data, it should provide consistency, meaning you have multiple nodes, 4 nodes. You query the data, all 4 nodes should see the same data, same value of that data. Okay? Like say, for example, your bank account has how much money in it. It should be a consistent view. Availability, system should always be highly available, meaning you have 4 nodes. Even if one node goes down, your system should appear to be available. Now there is partition phase. 4 nodes are attached to each other using a network. One of the node is not visible on the network. It gets disconnected from the network. How does your system perform? Like, does it feel that it is all down, or does it get confused? This is called split brain situation. With Oracle's RAC, we see the split brain sometimes. And also, the CAP theorem says you can pick only 2 of these 3. You cannot have a system which has all 3, right? So you can see the CP. So let's talk about consistency and availability. All your RDBMSs do that. Whereas CP is the consistency and partition tolerance. There are some databases like MongoDB which uses consistency and partition tolerance. And then the last category is the AP databases, which are availability and partition tolerance. Now, especially talking about Apache Cassandra, what it does is it gives you an option to have something called tunable consistency. You can say, for example, I'm storing this data. It has to be highly consistent. So I'm going to, for that particular SQL command you're writing or SQL command you're writing, you can say high consistency. But then you can, other places you can say, I don't care about consistency, let it be eventually consistent. Meaning within next 3 seconds, we'll have the data visible to all nodes and they're all consistent. There are a lot of inbuilt system checks built in to handle the consistency in case of AP systems. In the NoSQL world, we use mostly MongoDB, Redis, or Apache Cassandra, and React. So all of them have their own advantages and disadvantages. This is consistency thing. I'll leave the slide here. We can, leave the slide here. We can, look at it later. Now, in any case, like advantages and disadvantages, right? We talked about RDBMS, the same slide I showed you in the beginning. RDBMS is built as a general purpose database where you can do OLAP, OLTP, or any other warehouse kind of workloads. NoSQL is a purpose-built, meaning Cassandra is built for one specific purpose. MongoDB is built for one specific purpose. So you cannot basically make it a general purpose database. Yeah. Each of them have their own advantages and disadvantages, obviously. This is mostly Cassandra's selling slide. About resources, so basically I do a lot of YouTube videos, and the top one is my YouTube channel link.